Hey PChem, I have a short presentation on two of the sections from Chapter 7 today. Not a ton of math, but some good concepts about our continuing exploration of what's going on inside solutions. This chapter, of course, focuses on electrolytes in solution, and I'm going to start today's presentation by talking about more physics, the electric field. So I have a little equation here. I say the electric field at the surface of a charged sphere, doesn't matter if it's a cation or anion. I see a little error there already. Whoops, I can't erase that. A cation or an anion is going to be proportional to the magnitude of the charge. That makes sense. The electronic charge is a constant, and then the radius of the sphere. So this has an important impact on the solubility of electrolytes. A small ion has more concentrated charge than a large ion, so it can be hydrated by water more easily than a large ion. So since water is polar, on the left-hand side here I sketched a little cation. If it's, let's say, a +1 charge and it's a really small cation, that's really going to have an effect on multiple water molecules, in fact even into multiple layers of water molecules. There's a term called a hydration number of an ion that's directly proportional to the size of the ion and the charge. So a tiny ion, you can't fit as many waters around it. However, a larger ion with only, in this case, a -1 charge doesn't have the attractiveness as the smaller one because of that density. I say note that the radial extent of the ion's electric field has an effect on the so-called size of the hydration sphere. So what I mean to say by that is, and let me sketch a little bit on my PDF here, you can see I've drawn this cation, and this is kind of representing a small, densely charged cation. Notice how I have the oxygens in kind of the second layer of the water molecules pointing toward the cation. This hydration sphere actually ends up being relatively larger than this anion. The anion has a lower density. It's still a -1 charge, but it's spread over a larger volume. So the attractiveness for the positive end of the dipole for water doesn't really seem to extend beyond the first layer. If you see me drawing this here, I kind of have a couple oxygens going toward it, or the hydrogens. Basically, this is indicating that the radial extent of the attractiveness isn't really making it into the second layer. So that's what we mean by the hydration sphere. Now, I don't want you to think that these spheres that I've just sketched out are like hard spheres. There is a dynamic equilibrium between the water molecules that are inside the sphere and the ones that are outside the sphere. Hydrogen bonds are constantly being made and broken, and even though the force may be toward that ion, there still are other forces present. There's a huge range in these lifetimes, basically the average amount of time that a water molecule will spend inside the sphere. Notice that the bromide, a really large -1 ion, water molecules are sort of fluttering in and out of the sphere all the time, 10 to the -11 seconds. That's pretty darn fast. Notice that as the charges get larger, you see larger ranges of lifetimes. So that means if you have these cations with +3s and +2s, the water molecules aren't swapping in and out of the hydration sphere as quickly. And that's what we mean by the lifetime. So a bulk property of any liquid is viscosity. You guys made viscosity measurements, I think, in lab earlier this semester. What happens if you have a salt in your solvent? Well, small or multi-charged ions have such a large radial extent, like the kind I sketched out in the previous slide, that they sort of thicken the water. They're called structure-making ions. So lithium, sodium, hydroxide, aluminum, these are either really small ions or ions with large charges. They sort of thicken water in a way because they're creating this large sort of posse of water molecules around them, and that makes the water more viscous. The viscosity of plain water can actually be lowered by so-called structure breaking ions. So I have written here nitrate and perchlorate are so large and diffuse and weakly polarizing that they have a net effect of decreasing the density of hydrogen bonds in the solution. So again, if you're sprinkling relatively large ions, rubidium nitrate, so really, really large, +1, really, really large, relatively large anions, they sort of break up the network of hydrogen bonds to such an extent that the viscosity actually decreases. I wrote out a little bit of table 7.2 here to again emphasize this idea about the hydration sphere. Notice again that the ions themselves can have a trend going from lithium to sodium to potassium. The ions themselves get larger, but the hydration sphere is in reverse. The lithium has a smaller, densely packed +1 charge. Its radial extent that it affects water ends up being larger. So this large hydration sphere will move through water more slowly. This measurement in the first column is that mobility, ionic mobility. Notice that the large hydration sphere correlates with the slowest mobility. The potassium, which has a faster mobility through solution, has the smaller hydration sphere. So note that mobility tracks inversely with the hydrated radius. So we're doing our thoughts about what's going on in a solution. And the next part I want you to think about is not what the ions do to the solution as a whole, but let's look at the individual ions and the forces on them. So sometimes I'll mention, like when I defined infinite dilute in the last chapter, we talked about an ion in solution or any molecule, any solute molecule, I should say, those weren't ions, any solute molecule that doesn't, quote, see another solute. That's what we mean by infinitely dilute. You could extend the same idea to ions in solution. If you have a really, really dilute solution of ions, the ions don't really see each other through the distance. But what happens when they do? What happens when ions are within a close enough range that they begin to feel a force between each other? I, of course, immediately think of Luke Skywalker when I see about feel the force. But for us, we're interested in the attraction between what I've drawn here as like a sodium ion and a chloride ion. Well, the base force is Coulomb's law. The Q values are the charges on the ions, so a +1 on the sodium and a -1 on the chloride. The denominator is this kind of mess of constants and variables. The 4 pi epsilon naught is a constant that helps us put this force in SI units. The E naught has this funny name called the permittivity of the vacuum. Sounds a very antiquated term. It's basically a constant that again relates to a charge being felt through space by another charge. The R squared term is the distance between the center of the two ions squared. So the left-hand equation that I've sketched here is Coulomb's law of just two ions attracting each other through a vacuum. We're not really dealing with a vacuum here. We're not dealing with a vacuum at all. We're talking about ions, quote, seeing each other or feeling the force through a solvent. So if I have just drawn little S molecules here, it doesn't matter what the solvent is. You could think of it as water. You could think of it as anything. That extra term that I've highlighted in green there, that little epsilon, is called the dielectric constant. If you think of it as multiplying the force by 1 over epsilon, you're accounting for the presence of that solvent. I use the word mitigate the ions from feeling the full force of the other ion. You could think of it as buffering, you could think of it as shielding. All these words say roughly the same thing. Take a look at this portion of table 7.3 that I reproduced. The two solvents that shield these ions from each other the most are the most kind of polar solvents, or the one there's more imbalance. Of course, water is a polar solvent. that has the effect of masking this charge about to 1/80th of what it would be if these ions were in a vacuum. H2SO4 has a lot of charge localization because of the oxygens, and so that even does a better job. It shouldn't shock you at all that a totally nonpolar solvent like benzene doesn't have as much of an effect on the attraction between these ions. One thing that our author Chang mentions is that these values are temperature dependent. Whoops, I forgot to write a word in there. Temperature dependent, which should make sense because if you think about it, a warmer solvent is less dense. When you heat up a solvent, it expands a little bit and there's more empty space between the molecules, so you're going to have net fewer solvent molecules in between, so the dielectric constant is going to go down. The dielectric constant, that little epsilon, will influence the local structure of the ions in the solvent. And what I mean by that is, as you put more of the ionic solute in solution, the ions can kind of start pairing up or not pairing up. So ions are said to be free ions, like in my sketch on the previous page, where you might have several layers of solvent molecules between the ions. Alternatively, ions can actually be thought of as ion pairs, where you have just maybe one or two solvent molecules or even no solvent molecules buffering the distance between them. When you have an ion pair, essentially that pair of ions goes through the solution as a non-conducting species, because what is conduction? It's the movement of charge. If you have a cation and an anion who are essentially going through life together as a pair, they're not, that really is a net zero charge moving through the solvent. It's not really, you're not conducting charge. Now there are two forces opposing either the formation, there are two forces opposing that lead to either ion pairs or free ions. The potential energy of the attraction that we just mentioned, basically that capital F term, that Coulombic force of attraction. Alternatively, there's kinetic and thermal energy of the ions themselves. As long as something's not at absolute zero, it has motion, and the motion can potentially be driving these ions away from each other. Sodium chloride, for example, won't dissolve in benzene because the ions are not solvated effectively by a solvent with such a small value of epsilon. The benzene molecules don't really care to be near an ionic, an ion, I should say, not ionic. The next section talks about the solvation process, but from the point of view of thermodynamics. So let's look at how the familiar thermodynamic functions treat ions in solution. First, let's do some vocabulary. So you see this little cycle here. Do you remember the quantity called lattice energy? That's the energy associated with blasting apart 1 mole of salt into its gas phase ions, basically equation number 1 in my picture. Our textbook uses a capital U naught to designate that value. Lattice energies are pretty easy to calculate from data like heats of formation, ionization energies, and electron affinity. I'm pretty sure Dr. Breen probably gave you an exam question in first year on how to calculate a lattice energy. So there's big tables of them, they're easy to get. The enthalpy value for 3, so that's the enthalpy of solution, can be measured in a lab very easily. Basically, you take a mole of salt, you put it in solution, you see if the temperature changes, and if you know the heat capacity of the solution, you could get the delta H of solution very easily. Equation 2 is harder to get, in fact impossible to get in a lab, but you can calculate it using Hess's law. That value of the enthalpy associated with the separated ion in the gas phase going into solution, that's called the enthalpy of hydration, or in an old-fashioned way, the heat of hydration. So make sure you know the two differences there. The heat of solution, enthalpy of solution, and the heat of hydration are two different quantities. You know the difference. So how do you do that practically? Well, you use some reference data. Here I have some reference data for sodium chloride. The lattice energy is 787. That's equation, that was process number 1. The enthalpy of solution was process number 3. That's 3.8 kilojoules per mole. You do Hess's law. You basically subtract equation 1 from equation 3, and you get equation 2. That's a lot of energy. So the delta H of hydration for 1 mole of sodium chloride is minus 783 kilojoules per mole. Now, in the same way that we were interested in the contribution of the individual ions to the conductance of a solution back in section 7.1, can we take this value we just calculated and split it apart into the different ion contributions? That's what we're going to do. I said, of course, we're going to try. Well, like other thermodynamic terms, sometimes we need to set a standard state value and then compare everything to it. Very high-level computer modeling gives a reliable value for this expression. So a proton in the gas phase going to a proton aqueous. Obviously, I hope you could see that would be a really, really difficult experiment to do. But you could do this in silico, they say, basically on a computer, and take a proton all by itself and compare its energy to a proton being surrounded by water molecules. You basically get this value. So the delta H of hydration of a proton is minus 1089 kilojoules per mole. You could also calculate the delta S of hydration as minus 109 joules per mole. So we're going to take those values and then use them as the basis to get other values. And essentially, I give you the plan here. So once you have the proton value as a place to start, you can use data for HF, HCl, HBr, and HI to get the fluoride, chloride, bromide, and iodide values. So again, if you had those molecular data, like the heats of solution, you can get the heat of hydration value, as I'm mentioning here. So then, once you get those, then you can get the values of lithium, sodium, and potassium ions from alkali metal halides. So table 7.4 lists standard values for the delta H of hydration and delta S of hydration. The delta H of hydration values are all negative. Water loves to hydrate ions, right? You may also note that there's a correlation between ionic charge and the radius, and the enthalpy. Smaller ions and ions with larger charges interact more strongly with water molecules, just like we talked about earlier when we were discussing the hydration sphere. For the entropy terms, delta S of hydration, the entropy component of process 2 from our cycle before, there is considerable ordering of water molecules around each ion, giving a negative value for each. I'll show you the table in a second. Note that these values vary with ionic radius. Finally, for a delta S of solution value, the entropy change that accompanies process 3, you need to be mindful of two opposing factors. The hydration process, which we just outlined as negative, right? It's going to become more ordered to have an ion among water molecules. And the entropy gain from the solid breaking up into ions in solution. So you got two things opposing each other. The ultimate sign of the delta S of solution term is an outcome of this headbutting, this competition. So you could get positive or negative values for this. Here's the table that I mentioned to you. Notice how at the top, each of the values are listed as negative. So all of these hydration values are negative, and all of these entropy values are negative for the ions. What about formation values? You remember, I hope, from our earlier thermal chapters that you can get the delta H of any reaction if you have the delta H of formation values. At the time when you set the delta H of formation values to elements as 0, you base everything off that. Well, what do you do with ions? So even though chemists are able to get reliable values for the delta H of hydration for H plus using a computer, we can't unfortunately do that for a delta H of formation. Remember what a delta H of formation is? It's the creation of 1 mole of something from its elements in their standard state. So getting a high-level calculation for a mole of hydrogen is not going to be as precise. So to get around this problem, we basically just make up a value. Sounds strange, but we could do it. Basically, we're going to say the delta H of formation of a hydrogen ion in solution, in aqueous solution, is a 0. If you set that equal to 0, then you could do the following. You can get an actual delta H from the lab, and this one says that this one's minus 167.2 kilojoules per mole, and you plug that equal to the heats of formation of the products minus the heats of formation of the reactants. Since the two reactants here are elements, and those are 0, those go away, Since we defined the delta H of formation of a proton as 0, therefore the heat of reaction that we measured in the lab is going to be exactly equal to the delta H of formation of 1 mole of chloride ions. That's minus 167.2 kilojoules per mole. Now, measure the delta H of reaction for another reaction, say this one, sodium solid with chlorine gas to give sodium ions and chloride ions. If you can measure that value, which I've just written as an X here, that's going to be equal to the delta H of formation of the products minus the reactants. We just got the chloride value in the previous step, so we could solve for the sodium value here. Okay. There's some important last paragraphs in this section. Table 7.5 lists the delta H of formation, the delta G of formation, and the absolute entropy for a bunch of ions. I'll show you that in a second. First, for these aqueous solutions, remember that the standard state, when you see these little knots, for solute molecules, which these are ions in water, the standard state is a hypothetical ideal solution of 1 mol at 1 bar pressure in which the activity is 1. Thus, the ions have no interaction with any other ions. Now, we just talked about the fact that that often isn't really true. What we're saying, though, is that we're defining this as the standard state, and I think you could see the future. We're going to come up with some correction term later in the chapter to get a value of a real solution. Second, all those delta HF values are relative to the proton value. The values of the delta G and the absolute entropy were determined by exactly the same process as shown in the previous slide. You set up an arbitrary value of 0 for a proton, and then everything is based on that. Because the other entropy values are pegged to protons, unlike absolute entropy values for neutral species, remember those were always positive because they were compared to absolute 0 being 0, these are compared to protons at 298. So here you can get absolute entropy values that are positive or negative for ions. The magnitude and sign are influenced by the extent to which they can order the water molecules around them. Remember that small, highly charged ions, they have the ability to order water, so their S values are going to be negative. Larger ions or single charges are going to have positive values compared to protons because they're not as solvent ordering as the protons are. I didn't find a ton of problems for this one, but the ones I did have that reply to this are 725, 726, 727. I actually included the key for 26 and 27 on the last key. Give 725 a problem. I should say give it a try, please. And it involves using data that's measured to give an unknown value. And I think it'll be instructive to pay attention and try to work on that one. All right, I'll see you on Friday. I hope you guys have a good day. Bye-bye.